few of you did. It'll be mostly that plus some new stuff. All right. So, on whatever day, Monday, I don't even know where we are anymore. We had started talking about temperature regulation, right? And so dealing with, this is what I want, temperature regulation in general, right? So this is generally an issue, but we said one of the biggest issues that we worried about with here is temperature changes much more easily and much more quickly in air, right, than it does in water. And so organisms have a much more difficult time and need to be more worried about their performance curves. So we ended class talking about how temperature, I remember that was our x-axis here. Okay, so body temperature of an organism is connected to their performance. And so remember we said performance factors for an organism can mean a combination of two things, right? My personal or somatic performance, my body performance, how well am I growing, right, and living, okay, and or two, how well am I able to contribute energy into reproducing, right, either in gametes or in literal offspring. Okay, so the idea when we think about these performance curves is at areas like peak, right, all of my energy or the vast majority of my energy, right, can go into me being a happy, healthy, successful organism, right? Anything I intake can either go into me being a bigger, better organism or into me being more successful at reproduction, one way or the other, right? As we slide off that peak, right, as I get too hot, this would be higher temperatures, or too cold, as we get into lower temperatures of my body, I have to invest more energy in not dying. Okay, I either need to cool myself or warm myself, and so the energy, one way or the other, needs to go into that. And if the energy is going into, say, cooling myself down, right, it can't go into being a happy, healthy, good reproductive organism. Right? We don't have an infinite amount of energy, so I have to parse that out one way or another. Right, so this was the key feature at the end of class when we were talking. Right? Any big questions about the relationship, cool myself down today, between body temperature and organism performance or survival as appropriate as we think about getting way down here into the edges of what we can tolerate? That part felt okay? Okay, so remember when we get beyond this, we start thinking about this from an organism perspective. We ended class talking about ectothermy. Right, so remember individuals that aren't making their own body heat, okay, but rather gathering it from the environment around them. Okay, so remember we always want to disentangle the idea of endo or ectothermy, right, from homeothermy and poikilothermy. Okay, so if I'm an ectotherm and I want to be somewhat at least homeothermic, in other words, I need to have a stable temperature. I almost forgot how to spell that for a second. Yikes. Okay. As an ectotherm, okay, I need to regulate that temperature, okay, using where I am in the environment, right? Because the environment is what's giving me my body heat. Okay, now air changes quite quickly. Okay, even if we're in our house, right? We can feel the heater or the air conditioner kick on, and that just sitting there is a blast of cool or hot air. Okay, that doesn't matter much to us because our body temperature regulates itself, so to speak. But if I'm a little lizard, okay, getting a blast of, say, AC on my face is going to drop my body temperature to the temperature of that AC. That's a problem. Okay, so if I'm a sweet little lizard, okay, wherever I am is the temperature of my body. So if I'm cold, I need to go somewhere warm. And maybe a hot rock in the sun. Same right now, right? Warm beach in the sand. To warm myself up. If I'm too hot, okay, I need to go somewhere to actively cool myself off, right? So I need to go into a shady space, maybe a cool dip of water, right? So I can pull that coldness from the environment and help it cool my body down, because it's not going to do it on its own. So this is what we mean by behavioral thermal regulation. Okay, the behavioral component is the movement. I'm doing a thing, right? And thermal regulation, literally to regulate temperature. Okay, this is all well and good, right? Lizards get up, walk around, make themselves warm and cool. But this only works for ectotherms. It helps to cool us, right? If I'm really warm, right? Walking somewhere shady will help cool at least my skin. But if I'm very, very hot, okay, my internal body temperature is not going to change significantly from doing that, right? Because I'm an endotherm. So I need other techniques that's going to help me do that. Okay, so there are lots of techniques that help maintain homeotherm. Right, so we want to look at homeothermy, right? Remember, organisms that require stable body temperatures. Okay, so what can we do? Because remember, as endotherms, most of us are doing something metabolic. All right. So here's what's going on inside us. Okay, so let's just focus on the top graph for a second. So most of the time, just hanging out, relaxed, okay, like we are now, maybe when we're sitting on the couch, right, binge watching Disney Plus. Okay. We have what's called the basal metabolic rate. Okay, in other words, the base or minimum amount of energy that you spend to maintain your temperature, okay, doing nothing. Not that you guys are doing nothing, right? But you're not running, you're not walking, okay? It's not at least ridiculously off temperature in here. So we don't have to put in any ridiculous amount of work, right? We're more or less relaxed, more or less comfortable. I always think this room is a little bit warm, but we'll humor it, right? All right, so as we look at our basal metabolic rate, or our line here, okay, so this is our flat line at the bottom. This is energy spent at rest. Or minimum energy, right? So this is what it takes to maintain your body temperature. As long as you aren't doing anything crazy. Nothing crazy is happening. This is our couch potato temperature. Comfortable you. Right? Because remember, your metabolism is going to have to control your temperature in some way. You're always going to have to invest some energy. That's its job. Okay, so this is the amount of metabolite or energy that we have to invest. Be a little different for everybody, but the bare minimum. With me so far? Now see that? Okay, so let's look just to the right of that. Okay, so we see my x-axis is ambient temperature, right? That means the outside temperature. Okay, and my y-axis is my metabolic rate. Okay, this literally just means, wow, that looks huge. Energy, let me just say, that's not gonna fit, spent, right? That's the energy I'm spending, or how much energy we're using. So as I look to the right, I'm gonna go ahead and change colors here. Okay. What we're saying here is we're coming out of our couch potato zone. And it's getting hot. Okay. Same thing as we look to the left, right? When I go to the left of my red bar, okay, we're still talking about temperatures. So if I go below my couch potato zone, okay, we've got lower temperatures, so it's going to be cold. Now the key here is we see as soon as we move into one of those too hot or too cold zones, right, we are increasing the amount of metabolism we're using, right, the amount of energy that we have to spend. Right? And that makes sense, right? If I'm in a space where it's very, very cold, okay, so my body temperature is dropping, I'm feeling chilly. In order to maintain my body temperature of 98.6 degrees-ish, okay, but it's very, very cold outside, okay, I'm going to have to invest more and more and more energy, okay, to fight off that coldness. Whereas if I happen to be in a room that's already warm, I don't have to spend as much energy doing that. And by the same proxy, if I'm in a room that's very, very hot, and I start to sweat, I'm very uncomfortable, okay, I have to start spending energy to cool myself down. So we call our couch potato zone then, our happy, snappy, I don't have to work too hard place, the thermoneutral zone, right, so the TNZ. Okay, thermoneutral meaning temperature neutral, right? The zone at which I don't have to work hard. It's not too hot, not too cold, right? It's like the Goldilocks zone. So here we can see, right, where our pejus range is. Again, okay, so remember pejus range from our previous graph 2 slides ago. It's where we're tipping off of peak, right, where our graph is coming off of the top of our parabola. Okay, but we're saying there, it's starting to get too hot or too cold for me. I can't invest in myself anymore, or I have to start investing in cooling or heating myself. Okay, we can see those here as well. Okay, where we see these lower and upper critical temperatures, in other words, where we see our bends in our graph, where we leave our TNZ, right, and switch to these too hot or too cold areas, are where we see these beginnings of our pejus ranges. All right, so here's our key, right? This is what it looks like. We want to be in our thermoneutral zone. We want to invest as little energy as possible. And anytime we get out of that thermoneutral zone, right, we get too hot or too cold, Right, we see we have to increase the amount of energy that we invest, right, in order to get back to or maintain the appropriate body temperature. With me so far? Feel okay? Right, and as always, if you're online, don't forget, right, that you'll have to use your mics to engage with me because I can't see you. Okay, so this is what's happening. Right, we have to invest energy. Feels kind of boring. So let's look at some examples of what exactly are we using that energy for, right? Let's look at some animals. That's what y'all are here for, right? Cute little animals. So if we get hot, right, what are some things intuitively that we do, or some organisms do, okay? So what are we putting that energy for, right? To good use, no doubt. So generally speaking, when it gets hot, right, the goal is some kind of evaporative cooling. Okay, so bringing moisture, right, or your blood closer to the surface to allow the heat to dissipate off of you. So there are several different techniques that organisms use. Not all organisms use the same ones, right? For example, sweating. We do the sweating thing, right? Get wet, right, and let the heat dissipate through the sweat in your skin. Very similar way that panting works, right? So using a large surface area in the mouth, still letting heat escape through that wetness within the mouth, which is very common in canid breeds and bear breeds. Or things like gullar fluttering. That's what I have a picture of here. Okay, so the gullar area is this like soft, large skin patch in birds. Okay, so they can sort of drop that loose, right? And it's a bit like fanning yourself, right? So there's a lot of blood vessels in that skin pouch. So when they open their mouth and shake that out, right, it's exposing all of those blood vessels to the air. And as the blood passes through there, the blood is being cooled. Very similar to when we see large-eared foxes. Right, the key behind the large-eared foxes is a large surface area by which, right, blood is exposed, right, the veins in the ears. And as the blood passes through those ears, right, it's exposed to the air and allows that blood to cool a little bit. Right. We see several variations on this, right? For example, most animals can't true sweat. But kangaroos, for example, will lick their forearms, right? So kind of faux sweat. Okay, so the licking is mimicking sweat, and it still then does that evaporation. So as the sweat evaporates, right, the cooling of that evaporation helps cool the blood in their forearms. And therefore, as the blood circulates through there, right, cools down the rest of their body. Smart little kangaroos. Okay, so there's infinite variations on a theme, right? But I'm spending both time on this, right, and energy. I have to create the sweat, right, create the fluids or whatever the case is to do any of these things. And that's energy I'm investing on doing this, not on myself. Same thing if I'm below the TNZ. In other words, it's very cold. Okay, I have to have a series of mechanisms that'll help prevent me from getting too cold, and I have to invest energy in these as well. So there's lots of different techniques that I can use for this, right? Some of which we are also familiar with. So I can invest in variations on insulation, most of which we're familiar with, right? Hair, furs, feathers. Okay. Blubber. Okay. All of these are different types of insulation. right? Most of which, right, these are not standard fats. Okay, so this is not as simple as eating more puts me in a better condition. That's also true and important. Okay, but okay, things like that are also separate. We also have what are called thermogenic, in other words, temperature-based mechanisms, right, at the cellular level. Okay, largely what we call shivering and non-shivering. Okay, shivering is an involuntary mechanism, right? So that's happening at a cellular and neurological level. So shivering is asynchronous, involuntary movement, right? So your muscles are contracting asynchronously. So instead of everything moving up at once and down at once, right, you get these asynchronous contractions, meaning your arms, your shoulders contracting, right? You can feel that, but everything, all of the different muscles in your arms, kind of just doing whatever at different intervals. And the key here is when you move your muscles, right, they get warm. Okay? It's a natural consequence. So when I shiver or when I move all of my muscles really fast, okay, all at once, it warms all of it up very quickly, particularly when it's happening in places like your core, right? So your shoulders, your pecs, your core, right? Your abs, right? Which is where we tend to really shiver. Okay, the key is it's trying to warm up, right, the center of your body. It's usually pretty effective if temporary. And we also see investment in non-shivering cellular techniques. One of the most common, which is what I have a picture of here, is brown adipose tissue. Okay, so adipose tissue in general means fat. Okay, fat in general is certainly good to help insulate. Okay, but brown adipose tissue is a different beast. So this isn't just simply I eat, I get fat, thus I am warm. Hooray! Okay, brown adipose tissue, which is what we see here on our guinea pig baby, okay, is a specific type of adipose tissue. And so when we put this type of tissue down, the key here is brown adipose tissue, as we see, have both more mitochondria, right, which makes things like ATP, okay, and it has more blood vessels through it. Okay, so this type of tissue can be more active, okay, and we're going to get more warm blood flowing through it. Right, and so we see in the images that this type of tissue tends to be very centralized, right, around important organs. So in this case, around things like the chest, right? So we're going to keep respiratory organs and circulatory organs with some increased blood flow to them. So we still might shiver our literal booty off, okay, but these will be things that will help keep particularly very small organisms, right, rats, rabbits, okay, and all of those organisms from freezing to death, right? So it's more common in those types of organisms. Not exclusive, but more common. You often hear this called as like the good fat, which is like a bad nutritionist standpoint if you want my point of view, but maybe don't get me started on that. Okay, any questions about generally the TNZ? Okay, what our metabolism is doing and what we expect to see as an energy thing, or questions about the examples of how we see these energetic investments going, right? What we actually are getting from this, right? Remember, this is not an all-inclusive list. These are just some good examples. using a couple of them myself this morning. All right. The last thing we need to talk about, I think it's the last thing, for our transition to land, as always, a little bit of pee, right? So remember, osmoregulation in general is always very important, and we spent quite a bit of time on this in our life in the water, right? And this was very important in our life in the water because we were exposed to water all the time, and we said, well, most organisms are osmoregulators, okay, as opposed to osmoconformers. I need to have a different concentration of salt and water than the water around me. And that made sense to us. So we talked a lot about, well, how do we do that? And then we said, well, most of our organisms are going to be dealing with things via osmosis. And so we had to worry about things like that. Scales and slime and chloride cells. It's a very complicated issue. Now, we don't have that problem anymore, right? As we walk around, we don't have to worry about osmosis sucking water out of us. Now, that being said, despite the fact that osmosis is largely not problematic to you and I as we wander the halls of UC, water and salt balance is still problematic, right? As we know, we still need to have some salt in our bodies. Right, this was a big conversation we had. I don't care that you memorize how much salt. Right, it's a nice little trivia feature. The key is we know that we have to have some salt in our cells. Right, salt makes our heart pump. Salt makes our muscles work. We have to keep salt in our bodies. And we know that we need water. Okay, but we are no longer immersed in either. Right, we just wandering around away from both on a regular basis. Okay, so this is the key from land, is we have lost our ties to salt and water. So we wander the earth. Some days it feels aimlessly, right? All land organisms will die without salt and water. Okay, so humans can only lose 12% of their water capacity. Okay, an adult human, okay, so an adult male human, most of the time if you go 3 days without water, you will die. And there's solutions. You can drink your own pee and all sorts of super fun stuff I know that you really want to do if this comes up. Okay, but it's not super ideal. Okay, in which case you can last like 7 days. Yeah, to drinking pee. Okay, but the reality is this still is a super huge problem for land animals. So we need to figure out still how to deal with this whole osmoregulation business. So remember when we left our last conversation, I said we were going to revisit this. All right, so let's just quickly follow along the left-hand side. All right, the key here was when we did pee, yes, pee, okay, or created urine. Urine is important, right, because its goal in general, or the goal of the kidney, is to take nitrogenous compounds, right, and all organisms have some kind of nitrogenous or nitrogen-based compound. Thanks to things like amino acids, proteins, nucleic acids, okay, are all going to break down nitrogen. And nitrogen's pretty toxic. So our bodies have to figure out what to do with that, and we have to package it up nicely and get it out of our bodies. Okay. Usually in here as well, we're also going to package up things like carbon dioxide and any extra water. Okay. Thus, pee happens. Yeah, pee. Okay, so salt, nitrogen, carbon dioxide, water. Okay. In whatever amounts our body doesn't want anymore. So when we did this in the water, yas fishy, we were able to dispose of this as ammonia. Right? Fundamentally bleach. Okay. Why was this okay? Why do fish pee bleach? The water dilutes it. Excellent. Right? So fish pee bleach. And this is okay for fish to pee bleach because when they pee, they're living in an aquatic environment. Okay? So as they're peeing, it's immediately diluted. So it's not really affecting them in any sort of toxic way unless you trap them in a tiny, tiny fish bowl and then they slowly sort of poison themselves. What's the benefit to peeing bleach?
More toxins.
So we're gonna, no matter what, we're gonna remove the toxins our body tell us to. So why would I pee bleach as opposed to literally anything else? It doesn't require energy. Perfect. Right? Bleach or ammonia is cheap. Energetically, super cheap to make. Right? So if I'm in an area where I can pee it and it's not going to hurt me, yes. Okay, remember, our entire body is a balance sheet. It's a giant Excel spreadsheet of an energetic budget. Okay, and fish can cut a corner here. We can save some energetic funds when we make pee because the ammonia is not going to hurt us. Nice as well. Right? It's just as good as any other pee. Now, as we move on to land, it's not going to work anymore. Right? If we pee bleach, we're now stuck in a house with bleach pee in it. That's not super great. Okay? And think about when all of this came about. It's not like modern plumbing was a thing, so you were going to sit in a cave and pee bleach in the corner. Not awesome. So, I'm going to pull my fish stuff off of here to clean it up a little. We had to have other ways to go about this. So, the second option then, which is the most common, is called urea. And this is the kind of pee we happen to have. Okay, so urea uses kidneys. And this requires far more energy to make. So we kind of all know what urea looks like, right? This is your classic yellow liquid pee business. Okay, now, this requires sort of a medium amount of energy to make. This is going to be the middle ground version. All right, so it's a little bit more expensive than ammonia, but it's not going to be the most expensive one we're going to see. All right, so there's a little bit of a benefit there. It's not super expensive. Okay. The plus side is it's not toxic, right? I just made the joke that you can drink your own pee. Okay. You could not drink ammonia. Fish couldn't drink its own ammonia. Okay. So I guess it's not going to like survive a Bear Grylls episode. That's too bad. The negative of urea is it's dilute, right? We know that we're peeing water to some degree here. And that's its own trick. The reason ammonia is okay, right, is because when they're peeing it, it's getting diluted in the water that they live in. We do not have that option. So we're not peeing into water, right? We're peeing into air. So our solution is, well, let's mix it with water inside our body. Right? We pee a really strong liquid. So we're taking all of those kind of nasty substances, we're taking a lot of our precious water reserve, and we're pre-mixing them in our body. Okay? So when we pee stuff out, it's already very, very dilute. Okay, that's good in that whatever we pee out is not very toxic. Okay? It's not expensive energetically to make. But what's my downside now? I lost a lot of water. Okay, this has cost me my water reserve. Okay, and that's a big negative to any animal that's got to worry, right, about a water reserve. Okay, so this is my key. Okay, I'm cheap. I'm very low toxicity. Okay, but I've lost all my water in the process to do this. Also, I can drink my own pee. Okay, so that's urea. With me so far? Feel good? Now, that's not the only option. Okay, our last option is uric acid. Okay, so for us, we're mostly going to see this in birds and reptiles. You rude little thing. Okay, so you guys have seen this before and probably not realized what it was, right? So when you're looking at like bird poop that's been landed somewhere, the dark stuff is the actual poop part. The runny white stuff is the urine. So uric acid is super weird, okay? So the key here is this is super concentrated. Okay, so remember our problem with the urea, or our complaint, right, is it's super wasteful. We're on land. Salt and water is precious, okay? And we're just dumping water at every instance, right, like we're bougie. Okay, so birds and reptiles have taken the alternate approach and said, hey, maybe we don't do that. Right, and we keep the water as much as possible. And so as we look at uric acid, they've basically done the opposite approach here and said, I don't want to dump the water. We're going to use every possible chance we can to keep all of that water. Right? So that's why it's so dense and thick. There's like no water in bird pee. So it's gross and sticky, right? Makes like a glue. Now, it's still very low toxic, right? If they wanted to, they could drink it. Okay. But here's the catch. Okay, remember, there's no perfect solution to anything. And we want to keep that in our head. So where's our trade-off here? So if I'm not going to make things easy, right, and just dilute the crap out of it, which is what we've done every step of the way so far, I'm going to have to pay for that. So their solution is good. It's conservation-based. We have low toxicity, right? We have low water loss, but this is expensive. Okay, this is pricey pee from an energetic standpoint. Right, so each of these have different trade-offs. Right, we're either toxic, we're expensive, or we're costly another way. Okay, this is it now. This is all three types of pee that exist, at least in the vertebrate animal kingdom. Okay. Just like everything else we've looked at, okay, there's benefits and disadvantages to each one. bite me. Yeah, I know. We're going to do that in a second. I just want to make sure I'm not missing anything. Okay, any questions about that? I'm just going to flip back really quick, make sure. Okay, so the very last thing I want to mention, and this will be where we stop then, is I keep saying the kidney. Right? You know, the kidney's doing all the work here. And the kidney does most of the work in almost all of our organisms when it comes to making pee. Right, so we call this the urinary system. And so this is really important when we're talking about homeostasis in general, right? So we say remove waste. Of course, we're talking about urinary waste in this case, very specific, nitrogen and water and salt wastes. Okay, so this is central to worrying about that osmoregulation, right? That saltwater balance. And so our urinary system is a multi-organ connected system, particularly when we're talking about coming on land. So we got to see a little bit of this this week, and we'll see this continuing in lab, right? So we start at the kidney, right, where all of the blood is going to filter these fluids, okay? The kidney is connected to the bladder via a tube called the ureter. Right? It doesn't do anything special. It's just, hey, carry all of this crap that's left, right? I don't want this here. Kidney does the filtering. I'm going to say yes, no, keep stuff. Anything we don't want then, it's going through the ureter to the bladder. The bladder is new, right? And so the importance of the bladder is basically saying when I have to pee, I can hold that pee. And this becomes important for two reasons, right? If I'm living in a cave or a house, okay, I don't want to just pee all over stuff, right? I don't want to pee on my bed. I don't want to pee on my offspring, okay? I don't want to pee in front of my house. I don't want to lead a predator right to my house, right? They can see and smell that stuff. So I want to be able to take that pee literally anywhere else. And this is the key behind the bladder, is having some control. Because remember, what we do is no longer diluted instantly. Okay, wherever it goes, yes, I'm sure, it goes. Okay, as soon as we are somewhere where we think is appropriate, hey, that's when we can pee, and all pee goes out then another tube called the urethra. I know that the ureter and the urethra look like the same word. I don't name stuff, okay? So this is one of those things that practicing will do well for you. All right, took me a hot second to get your Socrative up. Kept telling me it didn't want to change the room, so my apologies for the delay. I have a Menti up I didn't get up, so I'm going to pop that up on our class page because I do want you guys to get a chance to do that. It's a good way to practice the different types of pee. Wonder how many times I said pee today. So watch our class page for the next couple of days. There'll be lots of different resources for study and class engagement. And otherwise, once you have, there's so few of us, I guess, just once you have your Socrative up, you are generally good to go. Please have a wonderful day. Remember, when we take tests, you do not have to come to class, right? So you do not need to come to class on Friday.
Who won the house quiz for the last exam?
For exam 2?
Yeah.
I do not know. It should say online, though.
It's like, at least on my computer, it's like, it says like house quiz here, and then it's just like blank.
I will have to check. I'll have to go back and look. Oh, I'm still recording.
No, I never got to